Welcome to Ask and Learn.
So here in this question, firstly, let's try to imagine the situation here. So we have a vertical circular track and we have the ball here. Let's assume that the ball is here and there is spring plunger over here. It is compressed. It is compressed 0.08 meters. Now the motion of the ball will be like this and the forces acting on the ball will be, let's assume that the ball is here, and the forces acting on the ball will be the gravitational force, which is mg, the normal force, which is n, and one is centripetal force, which is acting towards the center of the circle, that is fc. Now, the normal force is the force that the track exerts on the ball to prevent it from falling. The centripetal force is the force that keeps the ball moving in circular path. When the ball is bottom of the track, when theta is 0 degrees here, theta is 0 degrees because it is making 0 degrees with the floor. Now the centripetal force is equal to the normal force. In this condition, the centripetal force is equals to the normal force. However, as the ball moves up on the track, the centripetal force decreases, and this is because the ball is moving slower and the radius of the curvature of the track is increasing. At some point, the centripetal force will become so small that no longer enough to keep the ball on the track. This is when the ball leaves the track. Now, to determine the ball must be pulled back and released so that it will begin to leave the track when theta is 135 degrees. So we can use the equation the centripetal force Fc is equals to mg cos theta, where Fc is the centripetal force, m is the mass of the ball, g is acceleration due to gravity, and theta is the angle between the vertical, theta is the angle vertical, between vertical and line connecting the center of the track, line connecting, line connecting the center, line connecting the center. We can also use the equation of centripetal force, that is Fc is equals to mv square by r, which is the formula for centripetal force, where v is the velocity, r is the radius of the curvature. Now at the point where the ball leaves the track, the centripetal force is equals to 0, and therefore we can set the two equations above equal to each other and solve for the velocity of the ball. So mg cos theta is equals to mv square by r, and from here the velocity v comes out to be square root of mgr cos theta upon r. Now we can substitute this expression of v into the equation of kinetic energy, and the kinetic energy is given as Ke is equals to half mv square, where m is the mass of the ball and v is the velocity of the ball. So kinetic energy is equals to half m into square root of mgr cos theta by r square. And from here, the kinetic energy of the ball is equal to the potential energy stored in the string when it is released, and therefore we can set the two equations above equal to each other. We can set the two equations, that is half mgr cos theta by r square is equals to half into k into s, that is the distance, minus 0.08 square, which is the compressed length. Now, from here, the spring constant K comes out to be mgr cos theta upon r square upon s minus 0.08 square. And from here, we can substitute the known values into the equation to solve for K. So K is equals to 0.5 kg into 9.8 meter per second square into cos 135 degrees into 0.5 meter square into upon s minus 0.08 meter square, and this gives us k is equals to 4 sorry k is equals to 4.91 Newton per meter. Finally, we can use the equation of potential energy of spring to solve for the distance s. So the potential energy is equals to half Ks square. And as we know the value of K, that is, from here, S comes out to be square root of 2 Pe upon K, and plugging in the values, S is equals to square root of 2 into 0.5 joule upon K, that is 4.91 Newton per meter, and S comes out to be 0.20 meter, and therefore the ball must be pulled back and released to a distance of 0.20 meter in order for it to begin to leave the track when theta is 135 degrees. So I hope this answered your question. Thank you.